Softies and ex-Microsofties. Welcome to the afternoon session, the Microsofties and ex-Microsofties session. It's a great delight to welcome Byron. He's going to tell us about not what's on here, but distributed reasoning.
Thank you. So almost to the day. So it's been, in 3 months, it'll be 20 years ago I met Peter at, I know it because it was right after your ETAPS lecture in Barcelona. It's been a fantastic friendship and collaboration, so I also have some photos I thought I'd share for a moment. Lots of adventure. I like this shirt a lot. I've seen that actually a couple times now. Also, because I'm married to B, who is the CEO of Menoidics, I watched from the sidelines that whole interesting show as they made the company and sold it. But of all the things that I love about this friendship, one of the things I enjoy the most is running new work by Peter, and that can be in office, or it can be in a cafe, or it could be often in the pub. And so today I'm going to do that now on stage. So I'm going to run a new idea by Peter. And so why do I love running new ideas by Peter? And actually, this is mentioned at least once, if not twice, in the previous sessions. He gets ideas very, very quickly. Like if you're not communicating, it was Hong Sok, I think, said that if you're communicating your idea not very clearly, 95% of the audience will be like, "Huh, that sounds stupid," but Peter will get it, right? Peter will get it, and he will help you synthesize the way to say it that captures its beauty. And furthermore, he shares in your joy, right? He'll see something, think it's very cool, tell you how cool it is, and he's chuffed on your behalf. He reflects back the energy to you when you have something cool, and he tends to make those around him a lot better, which is also something that was mentioned. So that's what I'm gonna tell you about something today. So and because it's just after lunch, I've tried to make it. Unlike Patrick, it's not going to be absolutely riddled with formulae. So the context is that automated reasoning is big business at Amazon. I won't belabor the point, but enterprise customers, it's super important to them. There's tons of features available now in AWS that all use automated reasoning, and we're doing all kinds of proofs. And basically, every single category of product in AWS is either directly impacted by automated reasoning these days, or indirectly. So all services use networking, they all use virtualization, they all use storage, they all use cryptography, and we've done a lot of proof in that space. And it's driven under the hood. It's driven by theorem provers, right? And so what's increasingly happening inside of Amazon is we have something called it's a cloud scale software service called Amazon Trusted Solver, or we call it ATS. And this is and I'm going to use a little bit of Amazon lingo. This is a tier 1 pageable service staffed with solver experts and experienced distributed systems folks. And what that means, pageable, is that everyone carries a pager, and there's a rotation. And if you're a service using, because it's tier 1, so any service in AWS can use this service. And if this service isn't behaving in the way that they believe it should be behaving, they page the team, and the team gets involved, and we make it right. So this is a pretty big deal. So there's an SDK. There's all kinds of ways of interacting with it. I thought I'd show you just a little bit at the command line. So using the command line interface to it. So I'm going to call ATS. I'm going to start a solver task. I'm going to use CVC5. I'm going to run it on this file, and what you get back is some information, and in particular, you get an ID. And now you can use this ID to ask questions about your job that's now running in the cloud. And you can configure it in all kinds of ways. So for example, you could configure it to run 2 different solvers on the same job. So here I've configured it to use Z3 and CVC5, and CVC5 using, there's a particular flag on strings. And you can run it in compete mode, meaning like, let's take the first result, or you can run it in wait for all, which is like, let's make sure we're getting the same result. Okay. So this has all kinds of benefits for us. So first of all, it allows us to control the flags and how teams are using the solvers. So a lot of solvers will have corners that no one really has much confidence in. And so we really don't want customers making deployment decisions automatically based on the result of a theorem prover that's actually calling Z3, that's actually calling a decision procedure that Nikolai wrote and doesn't believe in even himself. So we need to make sure that we're calling parts of the solver that we believe in. And then also, like for example, CVC5 now produces auditable proofs. And so we've got all those features turned on. So that allows us to turn the screws on how teams are using it to make sure that they're kind of in a safe subset. Another, sort of important aspect is it collects telemetry for business decision making and these kinds of things. But importantly, and this is the thing I'm going to talk about, it allows us to start distributing reasoning. Okay, and so what do I mean by that? So here's all the solvers currently supported. Most of them are available to you. You could just download them on the internet. But this one is whoa, no, that wasn't my screen. So this one in particular I think is quite interesting because this is where we're doing the distributed work. Okay, so this graph is one of the most exciting graphs I've ever seen in my life. Okay, I'm going to tell you what it means. And so it's I know this kind of graph is a cactus graph. And how you read this is how you compare tools when they're solving many benchmarks. So this line, this top line, which is about this tool called Malab-Mono, that's listed on the name on the top right, is saying that at 200, so it can solve 250 benchmarks each in 200 seconds or less. That's what it's saying. Okay, and this one here is saying that in 200 seconds it can only solve about 100 benchmarks. So basically, you really want to, the best solvers are on the top, the worst solvers are on the bottom. And what this graph is the results of each winner of the international competition for the past 20 years compared apples to apples on the same hardware, the same benchmarks. And so you can see the progress of 20 years of SAT research here. So the blue solver is back from 2002, and then the higher up solvers are the later solvers. And then in a slightly unfair, and those are all sequential solvers. In a slightly unfair comparison, we're also comparing this new distributed solver. So this gives you some idea of how mind-blowing the distributed solvers can be. They're like leapfrogging 20 years of research. Okay, this is a graph from recent work that we've done on so that was distributed propositional satisfiability, and this is distributed satisfiability modulo theory. So it's SAT together with all the axiom with quantifiers and arithmetic and uninterpreted functions and these kinds of things. And again, the distributed solver is dramatically better. Okay, so let me say a little bit about what I meant by having this service allows us to start distributing. One of the problems with distributed solvers is that they require operation, right? If you're using 10,000 machines, guaranteed those machines are going to start going down. The network's going to fail. All kinds of horrible things are going to happen, and you're making deployments to it all the time. So things are just going to go wrong. You're going to need a team. Whereas with a sequential solver, you just compile, download, compile, and go, right? So that's sort of where things get kind of interesting. Okay, so what I'm going to do is I'm going to give you some of the ingredients. I'm not going to tell you exactly how we're doing it. I can pontificate on that a little bit, but I'm going to tell you some of the ingredients that allows us to get these kind of results. So the first one is, by the way, I have no idea what time it is. So who's keeping track? Okay, great. The base ingredient is portfolio solving. That was one I already kind of mentioned. You can run multiple solvers together, right? So you just basically make a bunch of copies, run different solvers, maybe set them up with seeds to get them to nudge them into different parts of the search space. Or alternatively, you can do something called shoveling. And then this horizontal scale that we get in the cloud gives us big advantages, right? So if we find SAT, then we know the original problem was SAT. If we find unsat, we know the original problem was unsat, okay? But that's 20 years old. So this next technique, this is, I know this from Marian Hula, who's a scholar at Amazon, and it's called Cube and Conquer, and it's how he's proved the Pythagorean triples problem. It's how he's trying to prove the Collatz conjecture. There's quite interesting work there, and then he's just proved the happy endings problem with this technique. So the idea is that you basically run a solver, and it's a special solver that computes predicates. So imagine we get row 1, row 2, etc. And then you basically specialize the formula with respect to all of the combinations of the predicates on the valuations. And then you run the solvers. And so you've now sort of carved up the space. So if they're all unsat, then the original problem is unsat. And if one of them is sat, the original problem is sat. Okay? And so this horizontal scale gives you more chances to succeed. And so here, for example, is an application of CVC5, the SMT solver, together with Cube and Conquer, together with a particular strategy for doing cubing. Okay. And so the approach is like we get 2x as many solutions. And this is kind of the interesting part. You're basically trying to statically decide how you're going to break up the search space. And if you do it wrong, it's not really to your advantage at all. But if you can do it right, things go really great. And so what we're doing is we're watching the proofs going on between the theory lemmas and then finding pieces that are mentioned often, and we're building predicates based on that. So the next approach, and this is how this tool Malib works, and also the SMT extension, is we basically do portfolio, but then we wire up all the solvers together. So basically they're sharing lemmas. The conflict clauses in the solvers are being shared across a bus. And this is an extremely effective technique. So if you find unsat in one, you know that the overall system is unsat because they're collaboratively trying to find a proof. And if you find sat in one, then you know the entire system is sat because it's really a collaborative proof. Then if we go way back into the history books, there's this really great work from Sanjit Sethi in his dissertation. This tool is called Euclid. It's kind of been lost, but I think it might make a comeback now. So the idea is, rather than doing this lazy SMT style, you do an eager translation. So for certain limited theories, you can do a direct compilation to SAT that's actually not an abstraction. And then you make one big call to SAT. And amazingly, eager plus Malib, that's this distributed propositional SAT solver, outperforms S3 and CVC5 sequential in some instances. So this is a couple of categories in the SMT comp, job shop and BCN scheduling. So it's not generally going to be better, but it can be better, which I find super interesting, that you can get rid of all of the theory reasoning. It's actually a much simpler system. Okay, the thing that we're quite excited about is this idea of storing lemmas, right? So you've proved something, and then 5 minutes later you're trying to prove something else. Could we use lemmas we proved before? Could we use lemmas we proved before to help advance the proof we're trying to do now? And this is taking advantage of often, like you try and prove a program, or maybe you do prove a program and then you modify the program and then you rerun the proof. Often the program has not changed that much. So there's a lot of, or you've written a policy or a network and you've changed it and you rerun the tool. They're probably quite related. And so this is something we're extremely excited about, and we're getting some really good early results on. And then basically the idea is we just build cocktails out of all these approaches, right? So maybe we have a bit of eager and lazy, and they're communicating with each other, and maybe we do some different seeding, and then maybe we do a bit of cube and conquering, and some eager and some lazy, and then maybe we store the limits, which we've done a little bit less of. So that's basically the ingredients, and we now have this up and running, and we're getting really good results, but we have all these levers, and we're trying to kind of figure out and we're doing experiments to see what are all the best combinations. And so each day things are getting dramatically better. So that's to me very, very exciting. Let me tell you a little bit about some of the sort of things that we're worried about. How much time do I have now? 5 minutes, great. Cost. So it turns out that running this big system is going to be way more expensive than a sequential microprocessor, right? And an idea I'm quite charmed by is, let's say that you're building an application based on an SMT solver. Probably a lot of the jobs you're going to see are very similar. Probably you could characterize the kinds of jobs you're going to see as a suite of benchmarks. And imagine you were to go solve those suite of benchmarks in a distributed solver, and they very quickly find, there's good decisions happening. The reason that a distributed solver is so much faster is that you get the opportunity to make different decisions simultaneously, and the good ones rise to the top. You find shorter proofs this way. And so actually, after you've found a proof, you could look back at the decisions and perhaps synthesize a decision heuristic based on the proofs that went fast for those suite of benchmarks. So maybe we could then synthesize a local solver that has that decision heuristic based in, that actually just runs on a sequential solver much cheaper. So basically, you can think of the distributed solver as sort of like a synthesizer of sequential solvers that are going to be fast and tuned for that domain. Another sort of difficulty that we actually have, it's down to 5 milliseconds, because the networks in AWS are insane, right? So if you're putting these things if you're running them in AWS, you can get the latency of the call across the network and back and forth extremely, extremely fast, because we have really good people on the team of kind of figure out how to do that. But still, even then, people are like a little bit worried, right? So the idea is that maybe we make your local solver just a member of this fleet. So maybe your laptop is just a temporary member of this ATS fleet, and for the fast jobs, they'll get solved even before ATS gets warmed up. But for the slower jobs, the ATS will end up solving them. So in that way, we get the telemetry, but you also get the speed of basically feeling like the solvers on your local machine. So a big issue. So we have this sort of huge opportunity. So strings, quantifiers. So some domains turn out to be really a pain in SMT. I'm not going to lie to you. But this sort of cloud native solver gives us some opportunities. So for example, we build new data centers all the time, and usually when we build them, we actually have a month or two before we start taking customer data on them. We burn them in. So actually, we can run big jobs on those data centers. So why are strings hard? Strings are hard because of the natural reduction to automata explodes, because if you complement the automata, the whole thing blows up. And I'm waiting for the music. And so what if we were to go and just brown out a data center and compute as many complements as possible and store them and keep those limits, so we wouldn't have to compute them at runtime? That's something we're getting some early cool success. So the other thing is, like, it's my belief that quantifier instantiation heuristics could and should take advantage of this cloud native distributed environment. And finally, finding variability risk is a big deal. So what we can do is we can run the same job with different seeds, and then, oh, look at that. This one took a really long time. So that's a warning to people using the solvers that if you're for example using Daphne, that you may risk a small change to your code making that proof blow up. And so this is an application of ATS that I find quite charming. And then finally, I'll say that proof production is very important to us. Yeah, I know. And we are producing proofs in the cloud distributed. So thank you very much. Happy birthday. Here's to many more years of adventure and friendship.
Cool. Can we squeeze a question in while Matt sets up, if Matt's around? Yeah, because they're going to have to reset the AV.
So I really like that you've gone to the old techniques, haven't forgotten them and mined them, and found that some of them work better than maybe people had thought, right? But it makes me wonder, like, so you're beating the old tools by a certain percentage, a big percentage. Is this mostly down to, suppose you use Amazon Resource to hire some smart people, then you use Amazon Resource for compute. Is this amount of win inevitable given the Amazon Resource, or plus the fact that you've hired smart people? I mean, is there an aha about, to use Philippa's term, is there an aha step here, or is it hiring smart people, use Amazon Resource, win?
It's largely a business innovation. It's the idea of a flywheel funding research forever. So the vision was, it like George Orwell said, the future is a foot grinding your face forever, right? So we build a large distributed system that's kind of slunking, kind of slow, and then we just forever replace its parts, lowering the cost, lowering the latency forever. And each one of those is technical innovations, but it's being driven by a much larger, more important business innovation.
Okay, cool.
Okay.
We'll go on then, quickly.
The benchmark thing with many processors in parallel running the same thing and finding proofs and everything. So you have a benchmark with yes or no answers and timings and decisions being made all the time. That seems like the dream scenario for reinforcement learning.
Yes, so we're getting billions of requests per day. And so it's basically every hour is like SAT-comp, SMT-comp.
So are you planning to do any reinforcement learning to learn heuristics and things like that?
So maybe we'll do that for Peter's 65th birthday party.
Thank you.
Okay. Later. Okay. So now second talk.